sort cosmic objects by two simple things: how they look and how they behave. A star is easy. It's a sharp, compact point of light. A galaxy is the opposite. Vast, fuzzy, sprawling, made of gas and billions of stars spread across enormous distances. Those categories have always been clean and separate, or at least they were, until the Webb telescope came along. Webb uncovered a strange group of objects that refuse to sit neatly in either box. In images, they look exactly like stars, tiny, isolated red pinpricks, no shape, no structure, just points. But when astronomers looked closer, much closer, the chemistry told a completely different story. These things aren't stars at all. Their light carries the unmistakable fingerprints of fully formed galaxies. They're dense enough to look like dots, yet massive enough to contain entire stellar populations. Small like stars, heavy like galaxies. Astronomers, clearly having some fun with the confusion, gave them a fitting nickname: platypus galaxies. Like the platypus, an animal that looks stitched together from different branches of evolution, these objects are an awkward mashup that standard theories don't know what to do with. The story begins with Webb's very first public image, the SMACS 0723 Deep Field. Overnight, astronomy changed. The image revealed a massive galaxy cluster acting like a cosmic magnifying glass, bending and amplifying the light from the universe behind it. Everyone's attention went to the obvious marvels: perfect spiral arms, smooth elliptical galaxies, arcs of light warped by gravity. These were familiar, reassuring shapes. They matched what galaxies are supposed to look like. But scattered quietly in the background was something else. Hundreds of tiny, faint red specks. You'd miss them in a heartbeat. They don't announce themselves. They don't look dramatic. They look like visual noise. In the past, telescopes like Hubble wouldn't have been able to resolve them cleanly enough to matter. They'd be dismissed as glitches, artifacts, or background junk. Even now, with Webb's clarity, most astronomers automatically filter objects like this out. The logic is practical. If it's just a single point of light, it's probably a nearby star in our own galaxy. Maybe a brown dwarf drifting through the foreground. With the flood of data modern astronomy deals with, you have to ignore the boring stuff to find the extraordinary. Algorithms do this filtering almost instantly. They're trained to hunt for fuzzy edges, extended shapes, glowing disks. A lone red pixel fails the test. Into the background it goes. But Hao Jing-Yan didn't follow that instinct. Instead of asking what looked impressive, he asked what looked empty. He deliberately focused on the things most systems were trained to ignore. Starting with roughly 2,000 compact red sources pulled from multiple surveys, Yan's team slowly narrowed the list. Eventually, just 9 objects remained. 9 that looked like ordinary point sources, but behaved in ways that made no sense. Visually, they were indistinguishable from stars. They even had diffraction spikes, the telltale 6-pointed flares created by the telescope's mirrors. That's the classic signature of something small and compact. The only thing that felt off was the color. These weren't just red, they were deeply red, pushed far into the infrared. And in astronomy, color isn't just aesthetics, it's a ruler. As the universe expands, it stretches light as it travels. Blue light becomes red, red becomes infrared. The redder something is, the farther away it is, and the further back in time you're looking. These dots weren't nearby stars cluttering the image. They were shining from roughly 12 billion light years away, from the early universe itself. And that's where the contradiction hits. At that distance, objects should be enormous galaxies. But galaxies shouldn't look like points. They should be fuzzy, extended, wide. Yet here were objects that were impossibly small for where they were located. Normally, a bright, compact source in the early universe has an obvious explanation: a quasar. A feeding, supermassive black hole can outshine an entire galaxy from a tiny region of space, making it appear star-like even across cosmic distances. That interpretation fits perfectly, until you test it. To confirm a quasar, astronomers turn to spectroscopy. They split the light into its component colors, revealing what elements are present and how fast they're moving. Around an active black hole, everything is chaos. Gas screams around the center at enormous speeds, smearing the spectral lines into broad, messy shapes due to the Doppler effect. Jan's team expected to see those broad lines. They didn't. Instead, the lines were razor thin. That single detail changed everything. Narrow emission lines mean the gas isn't racing around at extreme speeds. It's calm, stable, ordered. There's no violent gravity well tearing matter apart. That rules out an active black hole. The light wasn't coming from friction and collapse. It was coming from fusion, from stars. Young, hot stars, likely blue in their own time, but stretched into red by the expanding universe. Which leads to an uncomfortable conclusion. If the light comes from stars, then these objects are galaxies. And we're right back to the original problem. Galaxies are supposed to be big. The Milky Way spans about 100,000 light-years. Even tiny dwarf galaxies usually stretch across thousands. These objects, however, pack the mass of 1 billion suns into a region just a few dozen light-years wide. Picture taking every star in a major galaxy and crushing them into a space smaller than a typical star cluster. In our neighborhood, stars are separated by about 5 light-years. Here, they'd be almost touching. If a planet existed inside one of these galaxies, the night sky wouldn't be dark. It would be a solid blaze of light in every direction. That density explains why they masquerade as stars. They're galaxies compressed into something that, from across the universe, looks like a single point. And that breaks our rules. According to standard models, galaxies start out fluffy, loose clouds of gas that slowly condense over time. We have no explanation for how something could form this dense, this massive, and this compact without instantly collapsing into a black hole. For decades, astronomy has told a clear story about how galaxies are born. These objects suggest that story might be missing a chapter. This framework is known as the hierarchical model. It paints the early universe as a chaotic place filled with small, irregular clumps of gas and dark matter. These clumps drifted, collided, and merged. Small structures combined into slightly larger ones, which then merged again. Growth happened through repeated, often violent encounters. You can picture it like building a snowman. You start with a tiny snowball, roll it around to gather more snow, then smash another lump onto it. It works, but it's messy, inefficient, and slow. Gravity needs time to do its job. Collisions are random. You can't schedule them or speed them up. Building something large and organized takes billions of years. And that's exactly why these dense red objects are such a problem. We're observing them as they existed only about 600 million years after the Big Bang. On cosmic timescales, that's nothing. It's the universe's infancy. The hierarchical model simply doesn't have enough time to produce galaxies this massive and this compact so early. By the rules we've trusted for decades, these galaxies shouldn't exist. They're too big, too dense, too mature. They look like grown adults standing in a nursery. That contradiction forces astronomers to rethink the entire process and consider an alternative pathway: quiet accretion, also known as cold mode accretion. In the standard picture, gas falling into a galaxy heats up, forming a hot halo that takes a long time to cool before it can collapse inward and form stars. But the early universe was different. Everything was denser. Models suggest that cold streams of gas could slip past that heating phase entirely. Instead of slowing down, the gas flowed smoothly along filaments of dark matter, like water rushing through pipes, plunging straight into the galaxy's core. No traffic, no friction, no delay. This allows a galaxy to grow from the inside out. Rather than sticking material onto the outside, you're pumping it directly into the center, more like inflating a balloon than assembling a pile of parts. That explains the extreme densities we're seeing. Gas floods a tiny region, igniting an intense burst of star formation. Billions of stars are born almost simultaneously, packed into a remarkably small space. The result is a brilliant, compact core that outshines everything around it. This is why these objects look so strange. They aren't fully formed galaxies yet. They're seeds. What we're seeing is the birth of an ultra-dense core that may one day become the heart of a massive elliptical galaxy. Over time, they may draw in more gas, build extended envelopes of stars, and expand into the fuzzy shapes we recognize. But right now, caught at this precise moment, they exist as compact nuclear star clusters, quiet giants that grew rapidly while the rest of the universe was still waiting for its first major collisions. This efficient, silent growth bypasses the need for billions of years of mergers. It solves the timing problem. It reveals a fast-track method for building galaxies that we hadn't fully appreciated before. But the most unsettling realization isn't just that these platypus galaxies exist. It's that we've probably been overlooking them for years. In science, we tend to find what we're looking for. Build a telescope to find spiral galaxies, and you'll catalog spiral galaxies. Train software to remove stars, and it will eliminate anything that looks like a sharp point of light. That shortcut is necessary. The sky is crowded with stars from our own Milky Way, and astronomers usually want to clear that foreground clutter to see deeper into space. For decades, we've taught our machines that point sources are noise, so they ignored them, which means there's likely a ghost population hiding in our archives. These compact galaxies mimic nearby stars so perfectly that they were filtered out of countless surveys. We assumed that anything so small had to be close. We assumed distant galaxies had to look faint and fuzzy. By defining galaxies by their size, we blinded ourselves to galaxies defined by their density. James Webb gave us a wake-up call. In a single deep field image, an area of sky no bigger than a grain of sand held at arm's length, Haojing Yan identified 42 of these objects. That's staggering. If you find 42 in a patch that tiny, they can't be rare. Scale that up to the whole sky, and the numbers suggest millions of these compact galaxies scattered throughout the early universe. They're not anomalies. They may be one of the dominant forms of early galactic structure. That forces a rewrite of the cosmic census. We once pictured the early universe as sparse and quiet, with only a few bright galaxies slowly lighting up the darkness. Our timelines were built on that assumption. But if these objects are real, then the early universe wasn't empty at all. It was crowded, busy, efficient. We just weren't counting the right things. Now astronomers are going back through old data, re-examining archival images, searching for the tiny red dots that were once discarded. It's painstaking work. It requires unlearning decades of ingrained assumptions. We have to stop treating points of light as boring by default. Every dot now has to earn its dismissal. The universe hid an entire population in plain sight simply by making it look ordinary. That's a powerful reminder that our scientific categories are human inventions. The universe doesn't care about them. It produces what physics allows. If something looks like a star but behaves like a galaxy, then it's our job to change our definitions, not reality. The nickname platypus couldn't be more fitting. When Europeans first encountered the animal, they thought it was a hoax, a duck's bill sewn onto a mammal's body. It broke their classification system. The animal wasn't wrong, the system was. Astronomy is having its own platypus moment. For generations, we've taught that stars are points and galaxies are structures. The Webb telescope has shown us that nature isn't so tidy. It creates objects that blur the line, galaxies so dense they masquerade as stars. These aren't mistakes, they aren't noise. They're a natural phase of cosmic evolution that we failed to predict. That's why we build better telescopes, not to confirm what we already know, but to uncover what confuses us. The most exciting moment in science isn't certainty, it's confusion. That instant when a tiny red dot refuses to make sense. That's where progress begins. The early universe is turning out to be far more complex and alive than we imagined. It wasn't waiting patiently for structure to emerge. It was already busy, already building. Millions of dense seeds are drifting through the dark, carrying stories we're only just learning to hear. All we have to do is stop filtering them out, and admit that we don't yet know what a galaxy truly looks like.